periodic versus aperiodic waveforms, all you really need to know about, you know intuitively what the difference is. All you need to know is what the notation is. That's the notation for a periodic waveform. So as an example, that's an example of a periodic conjugate. I'm sorry, it's an example of a periodic waveform. And if that's the notation, the formula that is true for a periodic waveform is a periodic waveform is equal to itself when you translate it by any multiple of its period. So k is any integer and n is its period. And all it's saying is that it has this thing has a period, this particular example. In general, it has a period of n. This particular one has n equals 2. I promise that the rest is simple. Let's talk about energy versus power signals. I'm not talking about the energy or power in a signal, but I'm talking about an energy or power signal. And tell you, and all it is which one is finite, which one is infinite. So the energy of any signal, x of n, is, we write it as this symbol, and we define it to be the three equal signs. Is just a definition. It's the sum over your entire signal of x of n squared, which is equal to, in fact, I'm going to even simplify that one step further. It's equal to that. So for any value, so for every value here, for instance, this is 2, square it to make it 4, add it to the square of 1, which is 1, square of 2, which is 4, plus 1 plus 4. So that's the energy of the signal. And so you can see that this is going to be infinite for a periodic signal. It's going to be finite for a finite length signal. Now the power of a signal, which we're going to call the power sub x, is the average energy per sample. So in other words, it's the limit as your sampling group gets big of the energy in n samples all over n. So let me give an example of this. The book goes one step further. It says it's the limit as k goes to infinity of 1 over 2k plus 1, because that's how many, let's say if we summed our symbols from n equals minus k to plus k. 2k plus 1 is how many symbols we've got, that's our n. How many samples we've got, that's our n of x of, x squared of n. So let me just say why we're doing this. you have a power. No, I'm going to give an example first, and then we're going to finish this up. As an example, using this, the energy of this, if this is 2 and this is 1, starting at 0 would be 4 plus 1 plus 4 plus 1 plus, and so on, which would be infinity. The power of that, you can see it's repetitive, you can see it repeats. So we really only need to determine the power of 2 of these guys. So that's going to be the energy in the first 2 samples, which is 4 plus 1 over 2 samples. So that's going to be 5 over 2. And if we had done it for more samples, let's say we took it for the first 4 samples, that would be 4 plus 1 plus 4 plus 1. And now we've got 4 samples, and that's again 5 over 2. So in the limit, as we take find out how much energy we have in infinite samples divided by that very large infinite number, we end up with 5 over 2. So
Sir, does that only apply to an even sample rate, or are we only taking, at least in terms of power, only an even sample rate, or can we take an odd one and just be a different number?
Yeah, you could do an odd one. If you had something that looked like 0, 1, and 2, 0, 1, and 2. I think by odd you mean the period, not the sample rate. But here the power would be equal to 0 plus 1 plus 4 over 3, or 5/3. And that would be the same if we took it over just the first 3, or if we took it over the first 6, or as the limit gets big. So our signals, you can say it's a power signal if your P of the signal is finite, which implies that your energy will be infinite. So if you can talk about it as a finite number of power, infinite energy, it doesn't make sense to talk about energy because you can't do much with infinity. So let's say it's a power signal. All that means is it's a signal that goes on forever. We say it's a energy signal, on the other hand, if the energy is finite. But that means necessarily if the energy is finite and you take a look at that signal over an infinite long time, that the power must be 0. So that's an example of a finite length sequence. A sequence of length 3 will be an energy signal, an infinite length signal will be a power signal. It's a lot of words to get across, I think, a very intuitive concept. Questions on that before we finish the very last one with absolutely or square summable?
That example on the top right, why is it plus 4?
So the power is equal to, yeah, so your energy is squared.
Okay, I see that.
So, and the reason for that intuitively is that think of it as a voltage signal across a 1 ohm resistor. So you've got a 1 volt pulse here and you've got a 2 volt pulse here. Your 1 volt pulse will cause 1 amp of current to flow, which gives you a power of 1 watt. Your 2 volt signal will create 2 amps of current, which will create a power of 4 watts. So when we talk about the power or energy of a signal, we're always squaring the actual signal value. Last is absolutely summable. Versus square summable. And this is the fastest of them all. You can imagine that a lot of the techniques we do in electrical engineering will break down if you start putting signals that go up to infinity into them. And mathematicians make a big deal about whether or not Fourier transforms, for instance, converge, or Laplace transforms converge. And we say we don't care because anything that has finite amounts of voltage We'll always have a Fourier transform exists. We'll always have a Laplace transform exists, unlike some of these crazy things that the mathematicians use. For our signals, our version, our discrete time version of Fourier and Laplace signals, we need to know if those things exist. And they exist if certain techniques that we will use in the future exist only if our signal is square summable. And that just means that if you take the sum of the magnitude, the absolute value of your signal, if it's finite, it's absolutely summable. So a periodic, non-zero periodic is not absolutely summable. So that means it's going to be a power signal. A finite length signal will be always absolutely summable. Square summable relaxes that just a little bit. It says some techniques will work if we're just using real numbers, if we square, if this is true. And that's don't worry about that last definition. It's a very subtle definition that will only matter for a couple of operations, and I'll explain them when they come up. But this is important to note because some of these transforms require your signal to be absolutely summable or square summable to work.